In a previous screencast, we have already talked about acetylide ions, and I want to go back and touch on that and how these are super versatile in organic synthesis. Now, terminal alkynes, like the one shown here, are readily converted to an acetylide ion with a strong base, like, for example, NH2, or sodium hydride. Those anions are strong nucleophiles, and they're capable of reacting with electrophiles, right? Such as alkyl halides and epoxides. So again, the acetylide anion here is a nucleophile and is capable of reacting with an electrophile to form a new bond here. And this can be a new carbon-carbon bond, which is one of the reasons it makes this reaction so very versatile, is now we can expand our carbon chains. So let's talk about SN2 reactions here. Right? So these can undergo SN2 reactions. So once you do this as the first step, then the second step, for example, you can take your friendly alkyl halide and your acetylide ion, right? And those electrons attack the partial positive R group there, and then those electrons go on the carbon. And so I want to remind you, just from the SN2 reaction, that this is a really electronegative atom. This is a really, which withdraws electron density from this R group, making it partially positive. Well, when you have a negative ion here that can act as the nucleophile, it's attracted to that partial positive there. Now you need to follow your arrows to see what types of bonds you form. And so when we follow our arrows, we see now we have an RC with a triple bond, C, R prime. And the prime there just means that R group can be different or the same as the R here. It's just a way for us to keep track of where our generic R groups are going. Right? And then our leaving group. Now, a few things here. One of the things to note is that we can expand the carbon skeleton, but still keep the functionality of this triple bond. And so that means that for us, it's lovely, because then we can go through addition reactions. And so this can really open the door for us to have a longer carbon chain, to synthesize a longer carbon chain, and then still have different functional groups that are on that molecule. Now, let's look at some specific examples. The mechanism of substitution here is SN2, which is what we showed. And so it works fastest with primary and methyl alkyl halides, or it will also work with a benzyl halide here, because this will stabilize the carbocation that's formed through resonance. So we will also see that as well. Now, I want you to notice you're going to form the new carbon-carbon bond, and it's shown here in red. And your best double check is going to be to count the carbons of the two things that you are bonding together, and then count to make sure the end product has the total overall carbons as well. So, for example, I have 2 carbons here and 2 carbons here. I should have 1, 2, 3, 4 here. So it is a great double check. Now, so when we talk about SN2, that's going to be primary, methyl, right, or benzyl. And that benzyl, that's just an example here. And the reason that it'll work with benzyl is because it's stabilized by it. Oh, I hate to use pronouns because we can always get confused. Because the carbocation is stabilized by resonance. All right. Now, let's talk about elimination actions. Steric hindrance around the leaving group like what we would see here, causes secondary and tertiary alkyl halides to preferentially undergo elimination by an E2 mechanism. So if you have secondary or tertiary alkyl halides, right, they undergo elimination by an E2 mechanism. Right? And so an example of the E2 mechanism is shown here, where we have an acetylide ion that comes up here and it grabs that proton. These electrons come here to make a double bond, and the bromine is the leaving group here. We end up with our E2 product here. I'm trying to think if there's anything else I want to tell you. Nope, that's it. So just as a review, right? Secondary or tertiary, it's going to go through E2. Primary, methyl or benzyl will go through SN2 reactions. And so that's what we see here with this acetylide ion. Now, this carbon-carbon bond formation with acetylide anions is so helpful in synthesis, and it's used to synthesize a lot of natural product synthesis. So we've got two different reactions here. You can see here where the acetylide ion is added right here through a substitution reaction to give that triple bond. And then this is a marine natural product that we're synthesizing. And then the second synthesis we see where we have, again, a substitution reaction where that acetylide ion is added. And look at the functionality here. It's really awesome. So we can add that hydroxide group to it too. So now you've got a triple bond and a hydroxide in your longer molecule. And then after several steps, we synthesize this molecule as well. So this is incredibly versatile in natural product synthesis because it's a way for us to form new carbon-carbon bonds that contain a reactive functional group. And so that's very helpful for us. Now, acetylide ions can also react with epoxides. And so here's an example where we see that there's a backside attack at either carbon, and we end up attaching the acetylide ion and we get enantiomers. Now, I do want us to look at this mechanism. So I have a different example for us for this mechanism. Right, where these electrons come in, they attack that carbon, those electrons go back up on the oxygen, and it's a ring opening, and it gives you this product here. All right, and so we can see how that ring opens. Notice that this is a backside attack at the less substituted end of the epoxide. Now, let's look at a multi-step synthesis. As you can imagine, this is, as I mentioned, this is very versatile multi-step synthesis. And we talked about this at the end of the alkene chapter where we said, okay, you might have to do a synthetic or design a synthesis where there are multiple steps. One of the tools that we can use, or the methods we can use to do this, is retrosynthetic analysis. And this is just the method of working backward from a target compound, which is what you're trying to synthesize, to the starting materials. This is also written backwards. So when we think about this, normally we see, okay, look, we've got starting materials here. And we go through however many steps to get to the target. The target is what we're trying to synthesize. It's a word that we use instead of product here. And so what we want to do now is say, okay, I want to start here at the target compound, which is my final product, and I want to figure out what precursors I need to make to get back to the starting material. Notice that we are using a open arrow here, and this open arrow tells us this is a retrosynthetic analysis, that we are going backwards here. So it is a really important part of it, and you would draw it with 2 lines like that. So that's an example of that open arrow. Now, when we design a synthesis, reactions are generally divided into 2 categories. Those that form carbon-carbon double bonds, and then those that change functional groups. So convert one functional group to another. And so when you start working a problem, which we're going to do here in a minute, it's very helpful to go through a set of steps before you jump into the problem so that you can organize your thoughts. So the first step that you need to do is you need to compare the carbon skeleton of the starting material and the product. If the product has more carbon-carbon sigma bonds, right, than the reactant, right, the synthesis needs to form more bonds. Right? If not, then all you're doing is changing functional groups, right? Then my suggestion is to match the carbons in the starting material with those in the product right, to see changes. This is where a highlighter sometimes is really helpful, or a colored pen or colored pencil. I think that just really helps me. Then you need to concentrate on functional groups in the starting material and ask yourself, right, what methods that you know introduce the functional group in the product. If you have kept a running list of the different types of reactions that we've learned so far, this is where that is really helpful. My suggestion is to keep a notebook or to photocopy those or print those reactions in the back of your chapter that you can then use when you're working these problems, right? So one place where you have all your reactions, I find that to be really helpful. And then, of course, what kind of reactions does the starting material undergo, right? Then you need to work backwards from the product and forwards from the starting material, right? So you need to ask yourself, what is the intermediates, right? And that could be the intermediate precursor of the product. Always try to generate simpler precursors when you're working backwards. My suggestion again is the best syntheses use fewer steps. It saves time and it saves money and it saves what you have to do in the laboratory. So the best synthesis is the one that uses fewer steps because it's just easier on a lot of different levels. Then you need to check the synthesis by writing it in the forward direction, right? And so in the last chapter, we looked at kind of doing this retrosynthetic step, and we said, look, we can work backwards and you can work forwards. And so it's this kind of give and take or play with solving these problems. Now, here's another thing that sometimes can throw students off is sometimes we can get multiple syntheses, and these are all the same. They're great. Both of them are correct. And so you might have a synthesis and your neighbor might have a synthesis, but they both work, right? The other thing that you need to kind of look for is sometimes you can set up a synthesis, but you maybe have a synthetic trap or a reason that it wouldn't work. And so always go back and double check when you do these syntheses. So let's go through and do an example. So this is a problem, and it says devise a synthesis of the following compounds from starting materials having 2 or fewer carbons. And so I want to show you another way this could be asked. This could be asked this way: starting materials with 2 or fewer carbons, and then like that. So this is really helpful. This arrow here is really helpful because that's saying, hey, look, right? This is your precursor, right? Those are your reactants. This is your target or product. That arrow is what clues you in, that open arrow, that you need, this is your precursor and this is your target. If it's written like this with an arrow that's not open, then this is your target and this is your precursor. So I just don't want you to get confused by the 2 arrows, but there's 2 ways this problem could be asked. So I want you to be familiar with both of those. So we need to devise a synthesis, and we are going to work backwards here. And so when we look at this, all right, this is our target. This is what we're trying to achieve. And we need to count the carbons here to see how many carbons we need to add. So there's 1, 2, 3, 4. So this has 4 carbons. And if we start with a compound having less than or equal to 2 carbons in our precursor, we need to add 2 more carbons here. So we know we need to add 2 carbons to our precursor, right? And so the other thing we notice here is that we also have a carbonyl group here as well. And so we need whatever this compound is to have the functionality to get us to a carbonyl. Now, we haven't done much as far as carbonyl chemistry is concerned, and we also haven't done much as far as adding carbon-carbon bonds. The thing that we know that will add carbon-carbon bonds and keep some sort of functionality so we can turn something into a carbonyl is by using the acetylide ion, right? So if we are thinking backwards, the very first thing I would do is I would say, okay, hey, look, the last step needs to be to convert to the functional group. And so that means here, 1, 2, 3, 4, if I'm going to do an acetylide ion, I need a triple bond there, okay? Then, right, that means my precursor here needs to be this guy, right, with probably an alkyl halide, because we know how to do that. And then that means that I need to start with, okay, not always, and I mentioned it here, and I didn't really touch on it again, but I said, look, the last step needs to be to convert the functional group. If you are expanding the carbon skeleton and you were to say, hey, Dr. Pierce, I want to change the functional group right here. Once you change that functional group, you can't get your acetylide ion. So not always, but sometimes, most of the time, you want to expand the carbon skeleton first and then change your functional group. Because once you get rid of that triple bond, you lose all your reactivity. And so you don't want to do that at the beginning, okay? Because you want it to be there and to be able to react. So now we need to think about this in the forward reaction. Okay, we are going to start with this guy here, and we are going to add, I'm going to add sodium hydride. Right? You may want the NaNH2. Both of those would be fine. And that gives me that ion. And then I am going to react that with an alkyl halide. And let's say chlorine just happens to be my favorite alkyl halide. Let's say you really wanted to do a bromine here. That's also okay. Right? So we can have, this is one of those situations where we can have the same problem, but multiple answers. So that's going to go right there. So now we have right, 1, 2, 3, 4. 4 carbons, which is what we need. And then we need to think about what can we use to go from those 4 carbons that could give us a ketone here, right? And if we remember our triple bond additions, we know that we can use water, right, in the presence of acid and mercury because it is a alkyne to give us the carbonyl group there. The best thing to do here, the biggest thing to do here is organize the reactions that you know in some way it's easy to find them. Maybe it's a sheet of paper, maybe it's a notebook, maybe you print off the key reactions from the book, right, at the end of every chapter. Figure out what works for you so you can organize this information, or maybe it's flashcards, right, and you can use it. Then, right, my suggestion is to expand the carbon skeleton first and then change your functional group. And then you always want to go back and double check, right? I have 1, 2, 3, 4 carbons here. 1, 2, 3, 4 carbons here. This is where I expanded my carbon skeleton. There were 1, 2 carbons here, 3, 4. You are going to find counting those carbons seems really simple, but it's such a help in finding when you may have made a mistake. Right? And so it's a great double check. We are going to do this more in class. And as always, if you have any questions, please feel free to stop by my office.